Good morning, everyone. Happy Wednesday. Hope everyone's doing well today. So, today's a good day to do some catch up and review. And also, I wanted to go over the lab. Let me pull that up. If you have questions, again, now's the time. Ask them, ask away. So, I've just uploaded the lab for this week. So, it should track along nicely with what we're doing right now with our functional groups and just getting into our alkanes. So it's under here. And Chem 105 labs, now we have lab 3 open. I'm going to open the PDF. And so there's no video for this, but it should be fairly self-explanatory. So it kind of walks you through. So there's no like lab component, just going to be using our molecule kits. And so if you don't have a molecule kit, you can check one out from the school. Just contact me and we can arrange that. You can pick one up at either campus and that can help you. So that's the first part of this lab, is sketching through it and going through some of these isomers, both drawing them and constructing them. And again, I encourage you to use your molecule kits, at least to help you. Not required, but. And then the second part has us looking at WebMO. So I wanted to look at that part with you here now. Pull up these directions. And so it says to go to webmo.net/demo. So let's go there. And then so log into this demo server and it says use guest and guest. So go ahead and do that. Then it should pull up something that looks something like this. And then so we want to go over to new job, create new job for our builder. So now this pops up this little builder. So you have here your periodic table. So let's just start with methane because that's the first one. And you could click any element you want. So in this case, we want carbon. So I'll put that in the center. Then if we want to make methane, here's my hydrogen. And then you just click and kind of drag out and release. And then so the other thing that I would suggest is, so we're using, I don't want to go too much into all the theory and confuse people, but essentially we're using a pretty small basis set. And all this means is these different basis sets kind of make different assumptions and go into different depths in doing these calculations. So essentially, right, we're using computer software to model how the chemical actually behaves. And then we're going to compare this to our just kind of predicted geometries. But what I'm getting at is we may have to help it since we're using a pretty small basis set. These are small calculations, relatively speaking. You know, this is a free server, so we also have limited time. So that's also why we're kind of limiting our basis set. And so to help it, you want to draw your molecule as accurately as possible. So for this one, I'm going to try to rotate it like that. And so now I can get better angles. And it doesn't have to be perfect because, again, that's what it's going to be doing for you. All right, so now I have my structure, my methane, and I didn't do the greatest job of drawing it tetrahedral. So then we can do cleanup and kind of click that idealized. And so that should give it a better structure. Then click this little arrow at the bottom. I don't know if you can see that. My overlay is covering it, but it's down here at the bottom right. It says continue. Then we can click our engine to run these. So you could run Gaussian or QChem. I'll hit Gaussian. I think the instructions say QChem, but they should both give you the same results. And then job name, I would add your initials or something to it so you can find it in all the other jobs that are there. And then for the calculation, we want to do geometry optimization. So we want to see its geometry. Hartree-Fock is fine. And then you could kick this down to basic for the basis set. And then charge should be 0. And multiplicity should be singlet. So that's just singlet means we don't have any unpaired electrons. And then our job should be running, so you can see it running in the queue now. There's your name, whatever you name it. So then you can refresh this, and so look like it's already complete. So to view our job, we just click on this name here. And so now this gives us our optimized geometry. And so we can do, we want to check out the bond angle. So if you click this arrow here, and then you want to go in order. So if I'm measuring this angle, I go 5, 1, 2 here. And then so we get our bond angle. So there's 109.4. So that should be really close to what we expect and calculate. And then you can also click these bonds here so you can get the bond length. So that's 1.083 angstroms. And since this is methane, they should all be the same. So you can verify that. Nope, that's our bond angle, bond length. And so you just want to go through and measure all those and then write them down for your lab. And then you can go back and compare. How does this calculated structure compare to our kind of expected structure? And so I only have you model, some of the simple ones, but if you wanted to take it and, extend it beyond the scope of the lab and play with molecules and, run the calculations, see how they run, go for it. This is, open, free to use. That's why it's there for your exploration. So I think that should be fun. And of course, if you have any questions with the lab, just contact me. I'd be more than happy to walk you through the rest of the lab and help you with molecule kits and everything like that. So now I would just like to take questions, and then we'll go over some practice problems from the chapter. Let me know what you're struggling with. I think this is a good way to run the course if I give kind of the full lecture on Monday, and then we can leave Wednesday for questions. And as always, you can email me questions, and then I can, present them during lecture here for you if you can't make it live. Let's see. So let's look at a couple of these. So I wanted to go over this one. I don't think we explicitly covered it. So what happens when we have an alkyne and we react it with bromine? So now we want to react this alkyne with 2 equivalents of bromine. So what would our product be? And so alkynes are similar to alkenes, except now they can undergo 2 substitutions. So we can add 2 bromines to each of these carbons. So let's go ahead and draw out what that product would be. So bromine, bromine here. Now we just have a single bond. Bromine. Oh, I forgot a carbon. I was like, something doesn't make sense here. There we go. That makes more sense. And so similarly, we would have similar effect with hydrogen. So if we had an alkyne here, we could hydrogenate it. And so now we have to have two equivalents of hydrogen to fully react. So if we just have one equivalent, so we could do one equivalent of H2 and form the alkene here. So if we just had one equivalent, we would do that. But since we have two equivalents, this would fully make it to our alkane. So CH3, CH2, CH, CH3. Oh, something else that I've noticed that's been cropping up are these combustion reactions. I believe that we should have covered them previously, but I just want to make sure that we do a recap. So remember, our combustion reactions are just any general hydrocarbon. So carbon, hydrogen, potentially oxygen. Then you react it with some equivalents of oxygen, and the products are always carbon dioxide and water. So then for the first example in one of your practice problems, it has CH3, CH2, CH, CH3, 2 here, plus 8 oxygens, and it says complete the rest. And so this is, first of all, a really confusing way to look at this for a combustion reaction. I guess this is really helpful when we're trying to figure out these hydrogenations or bromination reactions. But if we're doing a combustion, we probably just want to rewrite it as its formula. So let me count. We have 1, 2, 3, 4, 5 carbons, so C5, and then H, so 6, 7. I think I miscounted 6, 7, 9. There we go, 12. H12. So remember, our formula should hold into play as well. So if this is an alkane, then the formula, right, is C N H2N plus 2. And so we have 5. And so we should have 12 hydrogens there. And so now we can go ahead and balance our equation, our reaction. And so I will say combustion reactions are kind of always the trickiest to balance. I would leave our oxygens for the end. So we could start, I would start just with our carbons and hydrogens. Might have to play around with it. So I'm going to start with 5 carbons here because I have 5 carbons. Now I want to balance my hydrogens next. So I have 12. So I'm going to put a 6 here. And then let's see. Does that balance it out? Maybe we weren't supposed to start with 8. That's my bad. So now we have 16 oxygens on this side, plus 5 times 2 is 10, plus 6, so 16, and so that works out. And if we hadn't known it was an 8 here, then we could have added it up here, seeing that we needed an 8 right there. So let's look at some other examples. So this builds off of what we were looking at, our ortho meta para substitution. So if you were given ortho dichlorobenzene, how would we do that? So let's break this down. So of course we have benzene here. So we'll start with that. Just writing my benzene ring. And then we have ortho dichlorobenzene. And so remind yourself, if we have a substituent here, this is ortho meta para. For our aromatic ring. So if we're looking at dichloroorthobenzene, that means our chlorines are going to be ortho. So we can draw them like that. And so another one that's similar to this, so if you were to see P nitrotoluene, so let's break that down. So now we're starting with toluene. So let's draw toluene out. So toluene is that methyl substituted benzene. And then, so now we want our nitro to be in the para position to our toluene. And so that's going to give us NO2 there and across from that methyl group. Let's see, let's look at a couple of others. Just more reactions. So the next one, let's look at this propene plus HCl. What's the product? So I would approach these first, because it asks you for the name of the product, but we need to break this down one step at a time. So let's write out what propene is. So propene, 3 carbons, then we have 1 double bond. Now we're going to add HCl to that. So let's start with our mechanism. I always like drawing the mechanism so we understand. This will take you really far if you understand the mechanism. So you have HCl. Double bond's going to attack. Don't forget all these electrons that chlorine has. And so these electrons can come over here. So now we have our chlorine. And then now we have to see which one's going to be more stable. And so it is more stable to put chlorine over here, since this is a secondary carbon versus a primary carbon. And now we can name it. So of course this would be 2-chloro propane. I just wanted to point out this reaction here. I guess let's back this up. Let's back this up for a second. So it gives us 2-methyl 1,4-hexadiene plus bromine. And so let's first start with just drawing what we're working with. So we have 1,4-hexadiene. So we should have 6 carbons. 1, 2, 3, 4, 5, 6. And then the double bond is going to be at the 1 and 4 position. So 1 there. So 1, 2, 3, 4. The other one here. Oops, I have an extra carbon. So that's why I always say count and double count. So 1, 2, 3, 4, 5, 6. I got carried away there. There we go. That looks better. And then, so I have 2-methyl. So that means it's the methyls group is going to be in the 2 position. So 1, 2. So there's my 2-methyl 1,4-hexadiene plus bromine. And so in this case, I would say let's add 2 equivalents of bromine, right? Because we have this double bond and this double bond that we can react with. And so we could completely brominate it. So bromine. So that would be our product there. And I guess let's name it. So 1, 2, 3, 4, 5, 6. Now this looks like 1, 2, 4, 5 tetra bromo, since we have 4 of them. And then now we could do the rest. So 2-methyl. And remember, bromo went first for alphabetical order, then methyl. So this is just extra information. So 2-methyl and now hexane. So let's look at a few more. So we have this reaction plus bromine. So what would we get? So don't forget the stereochemistry. So we would get two products. So bromine could be up like that, or it could attack from the other side. So those are not symmetric by rotation. You could also see just it drawn without the stereochemistry indicated. It's a little bit more proper to draw it with this racemic mixture so you understand what it is doing. I think I drew this mechanism wrong. Let's go back. I want to attack the chlorine first. Let's redraw this. Wrong mechanism. Wrong mechanism here. So let's look at this again. This will make more sense. So this double bond will attack the hydrogen. Now this makes sense. And so it's going to form this carbocation intermediate wherever it's more stable. So let's redraw this all. So it attacks the hydrogen. So electrons go to the chlorine. So again, the more stable carbocation forms. So we have a hydrogen here now from the electrons from our double bond. But we have chlorine hanging around, so this carbocation won't last long, and that's how we get our product. So that should make more sense now. Then kind of our last example. If we have an aromatic system, we add bromine to it in the presence of iron tribromide. What do we get? And we just get this singly substituted bromine plus HBr as our byproduct. Any questions, comments? Let's see if we can figure out this one. This is a little bit trickier. So now we have this molecule. So adding HBr, and it says 1 equivalent. So let's go through this. So the we have we have to decide which carbon here. So it's probably going to add to this carbon. So let's see what's going to happen. Which one's our most stable carbocation? Let me redraw this. So double bond, or triple bond, excuse me, attacks our hydrogen. So bromine is formed. So now you're asking yourself, well, which one is a more stable carbocation? So I would pick this one since this is a secondary, right? It's connected to 1, 2 versus this one. So let's draw that intermediate out. So we have our carbocation intermediate. Now our double bond here, C. And so now this has an H. So I didn't like how I drew that. And of course it already had an H. And so we have this intermediate here. Now our bromine, negatively charged, can come in and attack our carbocation. And so let's draw that final product out. So that would be your product there for that one. Are there other questions here? Let me look over, trying to see if I covered everything at least thoroughly enough so you can be successful. That's organic chemistry. It's pretty detailed. We're just trying to get a nice overview of it. So I think the quiz should be relatively straightforward. A lot of naming molecules as well. Let's do a couple of naming examples. Let's see what would be good. So let's look at one of the quiz questions. So it says, which of the following is an isomer of 2-hexane? Then it gives us a bunch of different answers. So first we have to see, what's the structure? What's the formula? And then how can we maybe make some other isomers? And so let's see how to approach this. So 2 hexyne, so hexene is 6. But we have our triple bond in the second position. So 1, 2, 3, 4, 5, 6 there. Let me double count. 1, 2, 3, 4, 5, 6. Okay. That works. Let's write our formula too. So what's going to be our formula? So we have C6. 1, 2, 3, 4, 5, 6. And then let's fill in all those hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll just double count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So now we have our formula here. And so we're missing kind of 2 degrees of unsaturation. And so it says, so which of the following? And then so our options are 2-methyl pentene, cyclohexane, cyclohexene, or cyclohexyne. And so let's go through these. So which one has the same formula? So 2-methyl pentene. So 1, 2, 3, 4, 5. 2-methyl. So there's our 2-methyl pentene. So let's see. Do we have the right number of carbons? 1, 2, 3, 4, 5, 6. Okay, let's count how many hydrogens. So 1, 2, 3, 4. So that's saturated. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so I can already tell that this wasn't going to be appropriate because we only had 1 double bond. So we only have 1 degree of unsaturation versus our 2 in our hexyne. So this doesn't look promising. So what about cyclohexane? So if we draw it cyclohexane, 1, 2, 3, 4, 5, 6. So again, 1 degree of unsaturation. So we do have C6, but then H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that doesn't look right either. What about cyclohexene? So let's draw that out. 1, 2, 3, 4, 5, 6. Add a double bond. And so now let's do our formula. So C6H. So 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10. So this looks promising, and I suspected that this would be it since we have our ring. So that gives us 1 degree of unsaturation plus our double bond. So there's our second. So that matches up with 2 hexyne there. So this looks good. And then just for completion's sake, so cyclohexyne, let's draw this out. Let me redraw this. Hard to draw. So our triple bond, 1, 2, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay, there's our cyclohexane. Let's draw our formula. So C 1, 2, 3, 4, 5, 6. H 1, 2, 3, 4, 5, 6, 7, 8. So we have now 1 degree of unsaturation from our ring, 2 from our triple bond, and so that gives us 1 too many, and so our appropriate answer is cyclohexene. Well, I think this is a pretty good stopping point. I'll hang around on stream in case there are any other questions. Otherwise, I highly encourage you to contact me for office hours, individual appointments, to help get yourselves caught up or to address any questions that may be lingering. So again, I'll hang around for a couple minutes or so. And so thank you. Have a good day.